Okay, so what we're going to do is go through the different exercises here: a side plank, a back bridge, a side bridge, and a hands and knees with a leg lift and arm lift, and work through the biomechanics. So we'll start with a plank, as you kind of see in this picture A here. So essentially, let's resolve the moments of the external loads around L5. So we have basically a force here acting up. So it's a force at the elbow. We have a force here at the toes acting up. It's the force of the feet. And then they have, then we have a mass of the legs. Put them here in the thighs. Force of the leg, and then we have here kind of a force of the trunk. Okay, so let's kind of resolve this all around L5 then. So here's L5. Here, so draw a line, got a straight line here all the way down. It's kind of weird. So we have a distance here, distance here, distance here, and a distance here. And so for the feet, we'll label the feet D1, the elbows D2, the legs D3, and the trunk D4. So we can see those are all causing moments. So the feet cause a moment this way. The elbows cause a moment this way. And we can see that both of those moments are tending to extend L5. Okay, so let's make extension positive. So they're both positive moments. And then if we look at the mass of the body, they're causing moments this way. So that's the moment of the legs. And then there's the moment of the trunk. So the moment of the trunk's acting kind of downwards. So both of the leg and the trunk are causing flexion moments, and let's make those negative. And so basically we know that we can sum our external moments. We know that it's going to be the moment of the feet, which is extension, so it's positive, plus the moment of the elbow, which is also positive, minus, because we know the leg is minus, it's flexing, so put the moment of the leg minus the moment of the trunk. And we could also write it out this way, where we have the force of the feet times D1 plus the force of the elbow times D2 minus the force of the leg times D3, and then minus the force of the trunk times D4. Okay, and that would give us our answer. So if we look at this, though, it becomes obvious that essentially the force of the legs is relatively equal. FL is going to be close to equal force in the feet, and that F elbow or F trunk is going to relatively equal the force in the elbows. So given that, we kind of know that the net moments, the extensors are going to win. Okay, so if the extensors win, then the internal moment for this would have to be flexion. So IM likely is flexion. Now let's switch to what's happening with the internal moment. So we kind of have a drawing here of our plank exercise. So we just calculated the external moments, and we're thinking we need to get IM equals EM. So we know that EM is extension. So we're assuming IM is flexion. And so basically, if we draw it out here, then we know that there's a force of the abdominals here, which could handle that for L5 here with an internal moment arm. We'll call that D1 there. And we know that the balancing the pelvis, that's what's required to stabilize the pelvis, is the force of the hip flexors here. And they have a moment arm essentially here for the pelvis. Okay. And so essentially the internal moment then is simply going to be the force in the abdominal muscles, because essentially the hip flexors are really only acting on the hip, not really L5. They're just balancing the pelvis so that the abdominal muscles can contract. Okay, times D1 will equal the external moment that we just calculated a minute ago. And then from that, we could go ahead and solve the force needed in the abdominal muscles. Let's look at what kind of EMG recordings we get with the abdominal muscles in this activity. So if we look here, what we can see is that the plank position is here. It's 1. This is the transverse abdominis, and really the activations are under 10%, so pretty minimal. The rectus abdominis, though, is up here in the 30% range on the right, and something fairly equivalent on the left. And so that's not surprising to us. And then if we kind of go down here more, we can see the external obliques is up in the 50% range on the left and right side. So it matches. We're getting a pretty strong abdominal contraction. Apply the same process to the back bridge exercise. So we'll start with our axis points. Our axis point is L5. And then we have the weight of the trunk here, acting downward. So the force of the trunk. And then we have here the weight of the legs acting down, force in the legs. Then we have some force here acting up, force of the feet. And then we have here a force at the shoulder. Okay, and so then we have moment arms to draw in. So let's draw some moment arms in. Okay, essentially so we need a center point, a reference point, so I'll put it through L5. Black won't work for everything, but let's do it here. So there's a distance there for the shoulders, distance here for the feet. Here's a distance for the legs, and then we can do it up here. Another distance for the trunk. And we can label these again, so let's see if we can be consistent. So I think we did D1, D2, D3, and D4. And then we can write out, like draw in some moment lines. So we can see the feet causing a moment this way. So there's a moment of the feet, and the shoulders causing a moment this way. So they're both tending to flex. And so basically we said flexion was negative in the last one, so we can keep it negative here. So we'll say flexion is negative, basically, and then the the legs are causing a moment this way, so moment of the legs, and the trunk is causing a moment this way, so moment of the trunk. Okay, and so essentially we'll say extension is positive, and both the legs and the trunk are causing extension. All right, let's write it all out. So here EM equals, basically here we have negative moment of the feet minus the moment of the shoulders plus ML, moment of the legs, plus moment of the trunk. Okay, so we can look at this and think, okay, we can draw it out, we can draw it out so we can actually calculate it. So we'd have, put a minus sign here. So we have force of the feet times D1 minus force of the shoulder times D2 plus the force of the trunk, okay, times D4, and then put the plus sign in there, force of the legs times D3. Okay, and that's good. Now, if we look at this, though, we're pretty similar situation where we know that the force of the feet is pretty close to equal to the force of the legs, and the force of the shoulders is relatively equal to the force of the trunk. So essentially, what we know is that the governing situation, if that, then the moment arms are determinant D1 and D2 are longer than D3 and D4, so the net effect is going to be, the external load will be flexion, so the internal load will likely be extension, or their internal moment, I mean. Okay, so now we're going to think about the internal moments that go along. What we have is an expected torque that we need to extend the back, so we can stay focused on the pelvis again. So draw a force up here, okay, which would extend the lumbar spine by tilting the pelvis this way. Okay, so we'll put extensors here, and then we'll draw a moment like this. Extensors, and then we'll put L5 here with the moment arm. Okay, and then we'll go and switch to blue. And essentially here we have a force of the erectors of the hip extensors here. Okay, which stabilize the pelvis. Okay, and help control how much extension you actually get in terms of motion, right? But they have this kind of symmetrical contraction to extend the hip and extend the back to lift your body off the ground. Okay, and so basically we could write the internal moment equation. So we'd have the internal moment here equals EM. We'll kind of slide down a little bit. Give us a little space up here. We'll write it up here. And so basically we get here, we get IM is going to equal the force in the extensors times this D1 here. D1 equals the external moment, which we just calculated. All right, so let's see how that jives with the EMG readings. Okay, so here's the EMG readings of the abdominal muscles. Start with the transverse abdominis. We can see right off the top is that essentially the transverse abdominis is, we're looking at the back bridge here, so this is going to be 1, 2, 3, 4, 5, so number 6. So this one here, so not much going on. And then with the rectus abdominis, really not much. It's like in the 10 or lower than 10% range, so not the rectus for sure, really. And then if we scroll down some here, and again we look at 6. Okay, in 6 you have about 30%. Here a little less for the abdominals. So some rotation in the obliques, or some contraction in the external oblique, which is not what we expected. And then we see some matching here from the so here's our rector spinae left and right, and then here's the multifidi, and we can see that for 6 we're up, around the 30% for the right, even higher for the left, and then for the multifidi we're in the 40 for the right and a little less for the left. So essentially what we're seeing is a pretty good match for rector. We're seeing that, which is consistent with our calculations, and then what we're seeing that's a little bit of a surprise is some small amount of co-contraction from the external obliques. So the only kind of explanation for that is that the external obliques can also kind of tilt or control the pelvic position, and so it seems to be really specific to the external obliques, because remember the rectus abdominis muscle contraction is not really changed or contributing that much, and so essentially there must be either a stabilizing function, but there's this kind of low level of co-contraction that's occurring, which has the consequence of increasing the compression forces. Okay, so now we'd like to move to the back bridge exercise, or the side bridge exercise. So once again, we're going to start by putting the axis in here at L5. Okay, and then we'll draw some of the different forces. So we have a force here at the feet. Then we have a force here at the elbow. Okay, then we can draw in the forces of the trunk. So I have the trunk here. And the forces of the legs, so up here in the thigh somewhere. This is the leg. All right, then we need the moment arms. Let's do those in red. So there's our reference point. So we can start drawing distances. So I have a distance there for the feet. There's my moment arm for the elbows. There's a moment arm for the trunk. And then we can go right here to do a moment arm for the legs. So let's name those again. D1, D2, I think we went D3 and D4. Okay, that's good. So then we can now use that to kind of think about our moments. So we have a moment here caused by the elbow force, so we have a moment elbow. Then we have a moment here caused by the feet, so we have a moment of the feet. So let's think about what direction those are. This is the person's left side, so we have left. Right? And so basically these moments are driving them into left side bending. So let's make left side bending a positive, and let's make right side bending negative. Okay, and so let's look here. So that's the elbow force and the foot force, but then the trunk here is driving, that moment is driving this way, so down, and then we have the legs doing the same thing, so the moment of the legs. But then again, we can kind of think about this, and essentially the forces of the trunk are going to be relatively equal to the force at the elbow, and the force at the legs is going to be relatively equal to the force at the feet. So what's driving the net moment is going to be the D1 and D2 moment arms are much larger than their respective D4 and D3 moment arms, so they're gonna drive the net moment. But when we're thinking about that, we can go and write the equation out. We can say the external moment equals, so we have the left side bending moments here. The moment at the elbow is positive, plus the moment at the feet is also positive, then minus the moment, the trunk, and then minus the moment of the legs. And then we could write it out like this. We could put F elbow times D2 plus F feet times D1 minus F trunk times D4 minus FL times D3. There we go. So now when we do the internal moments, we want to keep in mind that basically the total external load is going to tend to side bend the person to the left. So this is the winner likely of this external moment problem solving. Okay, so now here we've got a picture of our person doing the side plank, and we're trying to problem solve the internal loads, okay, or the internal moments that are balancing the external moments, and we decided that the external moments were causing, in this case this is our left side here up, and that was really the external moment was leading to this left side bend. And so we need an internal one that causes right side bending, so we need something that makes the body go this way. And so essentially we could do the same thing, put a force up like this of the side benders, and then at the hip we need something that abducts the hip, and so we could put a force down this way of abduction. Here's our L5 axis. So here's our distance here, D1 for the moment arm for side benders, and we know that the abductors are just stabilizing the pelvis and keeping it from rocking, so we can move the trunk. So then we could write out our equation in terms of the balance equation. We could write IM equals EM here. We could put FSB times D1 equals the external moment that we calculated just previously. And so essentially, in this case, we could think about what all the side benders would be for essentially what we're saying is that we need a right, this should be a right side bending moment, okay, and all the potential right side benders, okay, are the abdominals on the right side, okay, and the erector spinae muscles and multifidi on the right side. That's funny. That's some kind of dyslexic thing going on there. Okay, on the right side. Okay, and so that's basically our answer. Okay, so let's look at the EMG and see what we get. Okay, so let's here's our transverse abdominis. Which one are we looking at? The side bridge is here, so this is 9. And so for 9 on the right side, we see a pretty significant increase in contraction, but not on the left. For the rectus abdominis on the right, we see higher, but not significant, and then on the left, pretty standard low-level contraction, right? Okay, so that's fitting our kind of thinking so far. And then basically we have here for the external oblique, for the right side we have a really big increase, and then for the left we have very little. So in terms of the abdominals, that's following our expectation. How about for the erector spinae muscles and the multifidi? Essentially here, for the right side erector spinae, we have a pretty big solid contraction. For the left side, almost none, so that's consistent. And then for the multifidi, slightly more than the left. Here's my left, but really not impressive. So here we have the extrinsic back muscle producing much more for the side bending than the intrinsic muscles. So mostly accurate from the external load perspective. Okay, so let's apply this same process to a quadruped position for determining the external moments. Let me just get the this kind of graphic things going here. So we're going to do the same thing. Let's start though. Let's not. This hands and knees position has the arm and leg extended. Let's start by thinking about the problem without the hands and knees extended, and then we'll go ahead and add that. So let's make a two-stage process out of this. So let's do the same process. So we'll add L5 axis. We'll put our forces on here. So they're acting as if both arms are down now. So we'll have the force of the hands. Here we have the force of the knee. We're acting as if both knees are down. And then we have the trunk center of mass somewhere around here. Okay, so the force of the trunk. And then now, it's interesting because before we were putting the force in the middle of the thigh for the weight of the limb, and it's essentially, if we take this whole both limbs, it's really the center of mass of this segment below the L5 is somewhere really right around here, same kind of place, right? And so essentially it's acting down here on the and almost directly into the knee. So if we look at this and we just say, okay, for the quadruped position, what's the external load? We could do that to start this solving this, and this should make it a little simpler. So we can say, okay, so these moments here are acting here, and then essentially we have a moment arm here, and then a moment arm here. And what we can see is that in general, what happens in the quadruped position is the moment arms, let's label them again, so we have D1, D2, D3, and D4. When we look at this, it becomes kind of interesting. In this case, the moment arms at the ground reaction force here under the knee, and then the weight of the limb pretty much exactly cancel each other. So even though we draw the moments kind of similarly, we'd have like the knee moment would be here. Both leg moments would be here. Then we'd have the moments from the hands would be here. And then the moment from the trunk would be here. So we have the same kind of situation, right? But we get all that drawn. We can kind of, I think if I remember right, we made extension positive and flexion negative. So, but if we take all this into account, just for the quadruped position, we can see that essentially, you know, MK is going to be approximately equal to ML. So they kind of cancel each other, and that's in balance. So the external moment essentially equals FH times D2, which is extending the trunk, minus FT times D4, which is flexing, so we give it a negative. But we can also see that it's not very difficult activity, and so if you try this on your own, and you completely relax your abdominals, you'll fall into lordosis, and that falling into lordosis is because of this kind of whatever slight discrepancy there is in the positioning of D2 being slightly longer than D4, and there could be a slight offset for the legs, but it's pretty much a cancel. Okay, so basically there's a small amount of abdominal activation to keep the trunk straight in the quadruped position, and so we're asking the question, does it shift the balance toward the extensors if we extend the leg and the arm? Okay, so we've now erased some of the parts that we drew. So what we've done is made basically the problem a little more complicated by, instead of including both legs together, now we got to include them separately. So we've moved this one leg's moment arm back here, or its center of mass back here. So we have the left leg now here, and it now has a moment arm here. It's D5. And then we have the arm, the right arm, force in the right arm, and its respective moment arm here, which we'll call D6. Okay, and so the question now becomes: is there enough? The moment arms clearly are longer, and can cause, if we look at what moments these are going to result in. So the left leg moment's going to end up causing this kind of torque on the low back, or L5, and the right arm is going to cause this kind of moment. And so we can kind of see that there's potential for this to switch the balance and move it from a small abdominal contraction to an extension contraction. So, and primarily because D5 and D6 are so much longer than D1 or D2 or D3 or D4. So the question though is this enough mass of the arm and the leg to kind of cause this switch in the agonist, so that in terms of the external load would now be shifted from the abdominals to the back extensors. And that's our main question. So let's write out our complete kind of moment equation. So we have our external moments here. So we could write all the extension ones as positive and all the flexion ones as negative. So basically we would have M, LL, and then from before, okay, we would have our F of L, our leg here, times D3, so we'll put M, L, which is really the right leg. And then the other one that's positive is the trunk, so the moment from the trunk are all flexing, so they would all potentially contribute to recruiting the extensors. So I did that. I put their signs in wrong. Okay, and then we have the moment from the rectus the right arm. So then the ones that are extending, causing some extension, are the moment at the knee, and then the moment at the hands. Okay, and so basically we're counting on these two to kind of shift the balance from the standard quadruped position. And you could write it all out here with all 6 moment arms. Okay, but essentially let's look at the EMG recording now to see if just the weight of the limbs themselves can shift the moment equation and cause some recruitment in the erector spinae muscle, and to shut off some of the abdominal, the low-level abdominal contraction we would expect just from a standard quadruped position. Okay, so we're looking here at the hands and knees with right arm. We have right arm and left leg lift. So this is the yellow one here. All right, so if we are looking at the yellow for the transverse abdominis, okay, what we can kind of see is that here's 4 and 4, so there is actually some right transverse abdominis. Here's a 4 and 4. For the rectus, there's not much effect. And then also for the oblique, there's some small amount of activity. You can see here for 4 and 4, here and here. So that kind of consistent with the low-grade abdominal contraction. But let's see if we get any erector spinae just by putting our legs out. Is that enough mass to shift the balance? And essentially what we can see is that, well, for the right erector spinae here, for right here and here, there's definitely some increase for 4. And for the multifidi, there's definitely some small increase. So it's starting to shift the balance, especially if like we compare like the erector spinae activation during the standard plank. Here it's kind of better, all right. But what we kind of concluded in class is that in order to really shift the balance more, we would have to increase the mass on the legs, and therefore shift the external moment more toward the loading the extensors, so the external moment's flexing the trunk, so we have a opposing internal moment that's extending the back, and that would be the bottom line. Okay.